Welcome to the final video of chapter 6. We're going to talk about the pigeonhole principle, and we're also going to summarize the whole chapter. So we'll start with introducing it. We got a beautiful picture of 10 pigeons in 9 little boxes. And if you have 10 pigeons in 9 boxes, what can we conclude? That at least one box must have multiple pigeons. So to kind of, make this a little bit more general, if we have n items in m containers, and there are more items than there are containers, then at least one container has multiple items. And again, could be multiple, right? We could have done 3 in the first one and none in the second. Right? There's a lot of ways of doing this. How many ways are there of doing this? Well, that's a question for you, my counting aficionados. Okay, so there's actually another cool statement of the pigeonhole principle that I didn't include in the notes, but I wanted to talk about it. Another way of phrasing this principle is that there does not exist an injective function whose codomain is smaller than its domain. And we saw that a little bit in chapter 3. So before anyone gets chapter 3 flashbacks, this is a little optional side note. Let's say we had a function with some domain and some codomain. If this function's injective, what does that mean? Injective, remember, means that it's like 1-to-1. Okay? It's like the horizontal line test. Parabolas are not injective, right? Because injective means that if you have an output, there must only be one input that gets you to that output. So parabolas are not injective. So if you have think of this as outputs, right? If each pigeon's an output, this would not be injective because you have 2 pigeons for one input of the box. So if you have an injective function, the codomain cannot be smaller than the domain. This cannot be smaller than that, and it still be injective, right? If our domain is 1, 2, 3, 4, and our codomain is just 1, 2, 3, it can't be injective. There's no way to make an injective function from these 2 things. So that's another way to talk about the pigeonhole principle, which is fun because it ties in topics from our first 2 chapters on sets and functions. But the point of the matter is, you don't need to know that, but it's just fun. So here's another example of the pigeonhole principle. Let's say Jason wants to make 10 videos for chapter 6, and he has 11 topics that he's going to cover. Well, at least one video is going to have a topic pigeonholed into the other, and that's this one. Here we are. The book doesn't actually talk about the pigeonhole principle, but y'all are supposed to be introduced to it if you haven't been already. So here it is, nicely pigeonholed in this video. Okay, I think I'm a little out of order, but again, we can do something like this example. If we have 300 million users and each user has a 4-character lowercase password, I don't know who made these password requirements, but step it up. Can all users have unique passwords? Can all users have unique passwords? Well, if there's 4 characters of lowercase password, right? That's 26 options for the first, 26 for the second, 26. Yeah, we can have repeated. What's 26 to the 4th power? How many possible passwords are there? 456,976. Well, we have n people and m passwords. We have too many people, not enough possible passwords. No. People can't have unique. Really what I should have done is made this usernames. But it doesn't really matter. But can they all be unique? And the answer is no, by the pigeonhole principle. Right? We have too many things, not enough places for them to go. They can't be unique. All right. And this is really important in a lot of places where uniqueness matters. And you can a lot of times combine some counting things to determine whether you're going to run into this issue. And that's the reason why we're introducing this topic, right? Is for those kind of applications. We need a count to make sure that we're not going to have duplicates in those applications where duplicates matter. I think a lot of times this also pops up in like hashing functions, but I'm not as familiar with that. Okay, so let's do a quick review of all the kinds of counting that we talked about in this chapter. So we had kind of 4 ways of counting. We started off by counting like this. We said, okay, let's say we have a pin, right? And we can have repeated digits. How many pins are possible? And we just say, oh yeah, there's 10 digits and k spots, so we'll do 10 times 10 times 10, just like we did over here. That was kind of our first kind of counting. This is how many ways where the order doesn't matter. Sorry, specifically, order does matter. Repeats are okay, right? If we have a pin, we can do the pin 1, 2, 3, 1. That's okay, right? It's okay to repeat, and then we just multiply how many options for each one. They're all fundamental theorem of counting, remember? There's 10 options for the first, 10 options for the second. All 4 of these are fundamental theorem of counting, just manifesting in different ways. We also talked about n factorial, which is very, very similar. The only difference, and again, these are called permutations. The only difference here is that repeats are not okay. So if we're looking at a pin, for example, but you can't have repeats, well, you have 10 choices for the first, 9 choices for the second, 8 choices for the third, and so on. And as long as, you have that many options, 10 digits for 10 spots, then it's a full permutation. But you could also see a partial permutation. Maybe we had something like this. Again, maybe it's your pin. You have 10 options, but only four numbers in your pin. That would be 10 to the 4th falling, right? Looks something like this, which remember is just 10 times 9. It's still fundamental theorem of counting. You have 10 options for the first digit in your pin, but you used up one of them. So you only have 9 options for the second. You used up another one. You only got 8 options after that. And then the last thing that we talked about most recently, right, was combinations. N choose k. Well, this is like a partial permutation, but the order doesn't matter. I was going to abbreviate partial permutation, and then I decided I don't want to write that down. So it's like this, but order doesn't matter. So these are kind of the 4 things. So we're going to finish this chapter with a little exercise for you. I want you to look at this situation. You have 10 favorite books or favorite movies, however you want to play with it. And I want you to write a problem about putting books on your bookshelf or movies in a folder. I don't know. No, it doesn't work. It's got to be books. Okay. You need 10 favorite books, like it or not, read or not. I don't care. All right. How can you write a problem about putting books on your bookshelf for each one of these cases? So my goal for you is to pause the video and try to write one for each case. If you don't want to do that, if you're feeling a little lazy, then my second goal is identify which situation of counting is which. So here I have 4 problems. Some of them one's a partial permutation, one's a full permutation, one's a combination, and one is that first type where we can have repeats. Which one is which? How can you answer each one of these? Pause the video, try to come up with answers, and then we'll do it together. So if you can only have 1 copy of each book, so you physically have those 10 books right here, how many ways can you put these 10 physical books on the shelf? Well, there's 10 options for the first book on the shelf, and then 9, and then 8, right? This is just 10 factorial, which is some big number. I'm not going to write it out. Which one is that? That's a full permutation. That's number 2. That was letter A. Letter B, if you have 10 books and you want to put 5 on the shelf, how many ways can you do this if you don't care where they are? Just whether they're on or off the bookshelf. Oh, so the order doesn't really matter here. What matters is which 5 am I grabbing from my stack and putting on the bookshelf. That's going to be a combination. That's going to be 10 choose 5. We could calculate it using this formula. All right, and that's going to be a smaller number, right? Because it's still 10 factorial. We're just dividing by 5 factorial twice. So letter B is going to be combinations. And let's say in letter C, you have as many copies of each book as you want, but you have 10 favorite books. So if you wanted, you could make your bookshelf be Moby Dick, Moby Dick, Moby Dick, Moby Dick, Moby Dick 10 times. All right? Maybe you're just trying to be a library or something. I don't know. I mean, if that's the case, right? If you can have multiple copies of the same book, well, then you have 10 options for the first book, 10 options for the second book. Well, you have 10 options for all the books, right? So it's just 10 to the 10th power. You've got a lot of options if you can have repeats, right? This is the biggest number. The last question is if you have 10 books, you want to put 5 on the shelf. How many ways can you arrange them if the order matters? Well, this is a partial permutation. So that's going to be D, partial permutation. So we have 10. We want to put 5 on the shelf. That's just going to be 10 times 9 times 8 times 7 times 6. Those are 5 books. That's how many options there are for each book. Let me know if you have any questions. That's chapter 6 on counting. Next up, I believe we finish this this class on logic and proofs. Probably logic before proofs. That would make sense. That would be the logical. Okay. It's been a long day. Bye-bye.